Hello viewers. Welcome to the YouTube channel. In this video we will discuss class 12 or 2nd PUC Physics Chapter 1, that is electric charges and fields, from basic to advanced level. So watch till end, don't forget to subscribe the channel. Let's start one by one. Chapter 1, Electric Charges and Fields. Electrostatics is a branch of physics which deals with the study of electric charge at rest. Or, it is a branch of physics which deals with the study of force, electric field and potential due to electric charge at rest. What is an electric charge? Electric charge is a basic property of a body due to which the body attracts or repels another body. Charge is a scalar quantity. SI unit of charge is Coulomb denoted by capital C. Types of charges, there are two types. 1. Positive charge. 2. Negative charge. By convention, the charge on proton is taken as positive charge. The charge on electron is taken as negative charge. The charges were named as positive and negative by an American scientist Benjamin Franklin. Neutral body or uncharged body. The body is said to be neutral if it has no charge. Example, atom. Charged body or electrified body. The body is said to be charged if it has net charge. Example, ion. Polarity of charge. The property which differentiates the two types of charges is called polarity of charge. Note 1. When two bodies are rubbed together, then electrons are transferred from one body to another body. The body which loses an electron becomes positively charged body and the body which gains an electron becomes negatively charged body. 2. Addition of electrons gives negatively charged body and removal of electrons gives positively charged body. 3. Thales of Miletus was the first scientist who discovered the fact that an umber rubbed with silk or wool attracts the light objects. It was around 600 BC. 4. Mass of a body is always positive, whereas charge can be either positive or negative. 5. When the substance listed in column 1 are rubbed with the substances listed in column 2, then the substances in column 1 acquire the positive charge, and the substance in column 2 acquires negative charges. They are glass rod with silk cloth, cat skin or fur and ebonite rod, woolen cloth and umber rod, woolen cloth and plastic, woolen cloth and rubber. Let's look into brief explanation. It was observed that if two glass rods rubbed with wool or silk cloth are brought close to each other, they repel each other. The two strands of wool or two pieces of silk cloth, with which the rods were rubbed, also repel each other. Two plastic rods rubbed with cat's fur repelled each other, figure B, but attracted the fur. The plastic rod attracts the glass rod, figure C, and repel the silk or wool with which the glass rod is rubbed. The glass rod repels the fur. Conclusions. There were only two kinds of an entry which is called the electric charge. There are two kinds of electrification and we find that 1. Like charges repel and 2. Unlike charges attract each other. When a glass rod is rubbed with silk, the rod acquires one kind of charge and the silk acquires the second kind of charge. This is true for any pair of objects that are rubbed to be electrified. Now if the electrified glass rod is brought in contact with silk, with which it was rubbed, they no longer attract each other. They also do not attract or repel other light objects as they did on being electrified. Thus, the charges acquired after rubbing are lost when the charged bodies are brought in contact. Unlike charges acquired by the objects, neutralize or nullify each other's effect. Next, a brief explanation about electroscope for extra knowledge. Electroscope. It is a device used to detect the charge on a body. Gold leaf electroscope. It is one type of electroscope used to detect charge on a body. Construction. It consists of a vertical metal rod kept on a box. A metal knob is present at the upper end and gold leaves are attached at bottom end of a metal rod. When a charged object touches the metal knob at the top of the rod, charge flows onto the leaves and they diverge. The degree of divergence is an indicator of the amount of charge. Next, look into conductor and insulators. Conductor. The substance which allows the charges to pass through it easily is called conductor. Examples: all metals, copper, aluminium, Ag that is silver, Fe that is iron, etc., the human body, animal body and earth. Note: when a conductor is charged, then charges are distributed over the entire surface of the conductor. Insulator. The substance which does not allow the charges to pass through it is called insulator. Example: wood, plastic, diamond, glass, etc. Note: if some charge is put on an insulator, it stays at the same place. That is, the charge doesn't get distributed over the surface of insulator. Basic properties of electric charge. Point charge. If the sizes of charged bodies are very small as compared to the distances between them, we treat them as point charges. All the charge content of the body is assumed to be concentrated at one point in space. Next, basic unit of charge, or elementary charge, or fundamental charge. The charge on an electron or proton is called basic unit of charge or elementary charge. It is denoted by the letter E. The value of elementary charge is E is equal to 1.60292 into 10 to the power minus 19 Coulomb. Note: 1. Charge on electron is equal to minus E is equal to minus 1.602 into 10 to the power minus 19 Coulomb. 2. Charge on proton is equal to plus E is equal to plus 1.602 into 10 to the power minus 19 Coulomb. Therefore, magnitude of charge on electron and proton is equal. 3. Charge on neutron is equal to 0. 4. The least possible amount of charge that can exist independently in the nature is called elementary charge. Next we discuss about basic properties of electric charge. 1. Additivity of charges. Charge has magnitude but no direction, similar to mass. However, there is one difference between mass and charge. Mass of a body is always positive, whereas a charge can be either positive or negative. Charges can be added algebraically, that is, if a system contains positive charges plus Q1, plus Q2, plus Q3 and negative charges minus Q4 minus Q5 minus Q6. Then, total charges of a system or net charge is equal to plus Q1 plus Q2 plus Q3 minus Q4 minus Q5 minus Q6. Example: if a system contains the charges plus 5 Coulomb, plus 2 Coulomb, minus 3 Coulomb and minus 2 Coulomb, then net charge is equal to 5 Coulomb plus 2 Coulomb minus 3 Coulomb minus 2 Coulomb is equal to plus 2 Coulomb. 2. Charge is conserved. Conservation of charge states that the total charge of an isolated system remains always constant, that is, total charge of the isolated system can neither be created nor be destroyed, but there is a transfer of electrons from one body to another body. Therefore charge is conserved. Example: in unstable nucleus, neutron is converted into proton and electron. A neutron turns into a proton and an electron. The proton and electron thus created have equal and opposite charges, and the total charge is 0 before and after the creation. That is, neutron is equal to proton plus electron. According to law of conservation of charge, charge on neutron is equal to charge on proton plus charge on electron. 0 is equal to plus E minus E. That is, 0 is equal to 0. 3. Quantization of charge. The charge on a body is always an integral multiple of charge on electron. Quantization of charge means charge on a body can be increased or decreased in steps of E. Charge on a body is given by expression for quantization of charge. Q is equal to Ne, where N is equal to number of electrons added or removed from the body. Q is equal to charge on a body. E is equal to elementary charge is equal to 1.602 into 10 to the power minus 19 Coulomb. SI unit of charge is Coulomb, denoted by C. Quantization of charge was experimentally demonstrated by our Dr. Millikan through his all-drop experiment. Quantization of charge was first suggested by the experimental laws of electrolysis discovered by Faraday. The force of attraction or repulsion between two charges at rest is called electrostatic force. In short, the basic properties of electric charge. 1. The electric charge is conserved. 2. The electric charge is quantized. 3. The charge is additive. 4. Like charges repel each other and unlike charges attract each other. 5. Charge is scalar, its SI unit is Coulomb. Examples. If 10 to the power 9 electrons move out of a body to another body every second, how much time is required to get a total charge of 1c on the other body? Solution. In 1 second 10 to the power 9 electrons move out of the body. Therefore, the charge given out in 1 second is equal to 1.6 into 10 to the power minus 19 Coulomb into 10 to the power 9 is equal to 1.6 into 10 to the power minus 10 Coulomb. The time required to accumulate a charge of 1 Coulomb for every second B. That is equal to 1 Coulomb divided by 1.6 into 10 to the power minus 10 Coulomb per second. On simplification, we get 6.25 into 10 to the power minus 9 second. To convert from seconds to year, divide 6.25 into 10 to the power minus 9 second by 365 into 24 into 3600. Finally we get 198 years. Thus to collect a charge of 1 Coulomb from a body from which 10 to the power 9 electrons move out every second, we will need approximately 200 years. Next, Coulomb's law. State and explain Coulomb's law in electrostatics. Statement. It states that the force between two-point charges is directly proportional to the product of magnitudes of two charges and inversely proportional to square of the distance between them. The force is acting along the line joining two charges. F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. Explanation. Let Q1 Q2 is two-point charges. R is equal to distance between them. F is equal to force between Q1 and Q2. Therefore, F is directly proportional to Q1 Q2. Mark it as equation 1. Then, F is inversely proportional to R square. Mark it as equation 2. From equation 1 and 2, F is proportional to Q1 Q2 by R square. After removing the proportionality, we get F is equal to K into Q1 Q2 by R square. Equation 3, where K is equal to proportionality constant. That is K is equal to 1 by 4 pi epsilon naught. On substituting K in equation 3, we get F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. This is the expression for electrostatic force or Coulomb's law. Note 1. Epsilon naught is called permittivity of free space. SI unit is Coulomb square per Newton per square meter. The value of epsilon naught is equal to 8.854 into 10 to the power minus 12 Coulomb square per Newton per square meter. 2. To find the value of K, that is 1 by 4 pi epsilon naught, substitute values, that is 1 by 4 into 3.14 into 8.854 into 10 to the power minus 12 Coulomb square per Newton per square meter. We get 0.00899 into 10 to the power plus 12. On moving point for 3-digit, we get 8.99 into 10 to the power 9. That is on rounding we get 9 into 10 to the power 9 Newton meter square per square Coulomb. 1 Coulomb. Definition. 1 Coulomb is the charge that when placed at a distance of 1 meter from another identical charge kept in vacuum experiences a force of repulsion of 9 into 10 to the power 9 Newton. Or 1 Coulomb is the charge which repels another identical charge with a force of 9 into 10 to the power 9 Newton when placed at a distance of 1 meter in free space. SI unit of charge is Coulomb, C. Next, define 1 Coulomb using Coulomb's law. According to Coulomb's law, F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. If Q1 is equal to Q2 is equal to 1 Coulomb and R is equal to 1 meter, substitute in above equation, we get F is equal to 1 by 4 pi epsilon naught into 1 by 1 square. On substituting values of 1 by 4 pi epsilon naught, the final answer is 9 into 10 to the power 9 Newton meter square per square Coulomb. Define 1 Coulomb of charge in terms of current. 1 Coulomb is that charge flowing through a wire in 1 second if the current is 1 ampere. Next, Coulomb's law in vector form in terms of position vectors of two charges. Or show that the Coulomb's law agrees with the Newton's third law of motion by taking the position vectors of two charges. Consider 2-point charges Q1 and Q2, located at 2 points in vacuum. Let vector R1 and R2 be position vectors of Q1 and Q2 respectively with reference to O. From triangle law of vector addition, vector R21 is equal to vector R2 minus vector R1, and vector R12 is equal to vector R1 minus vector R2. From Coulomb's law, force exerted on Q2 by Q1 is vector F21 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R21 square into R21 cap. Force exerted on Q1 by Q2 is vector F12 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square into R12 cap. But R12 is equal to minus R21. Therefore, vector F12 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R21 square into minus R21 cap. From equations 1 and 2, we get vector F21 is equal to minus vector F12. The force exerted by two charges on each other are equal and opposite. Coulomb's law agrees with Newton's third law. Importance of Coulomb's law. 1. The forces exerted by two charges on each other are equal and opposite. Therefore, Coulomb's law agrees Newton's third law. 2. The force act along the line joining the two charges and hence these are central force. Limitations of Coulomb's law. 1. Coulomb's law is applicable only for point charges. 2. It is applicable when the distance between the point charges is greater than 10 to the power minus 15 meter. Note: important for CET, NET. Permittivity of a medium. Permittivity is the ability of the medium to allow the electric field lines to pass through it. Permittivity is defined only for dielectrics, that is insulators. Relative permittivity, or dielectric constant, denoted by epsilon r. Consider two charges Q1 and Q2 are placed in free space, that is air or vacuum, and separated by a distance of r. From Coulomb's law, F air is equal to 1 by 4 pi epsilon naught into Q1 Q2 by r square. Equation 1. When Q1 and Q2 are placed in dielectric medium, F medium is equal to 1 by 4 pi epsilon into Q1 Q2 by r square. Equation 2. From equation 1 and 2, Fa by Fm is equal to epsilon by epsilon naught is equal to epsilon r. Dielectric constant, or relative permittivity, is unitless, that is no unit, and dimensionless, that is no dimension. Value of dielectric constant depends on the temperature. It is also called as specific inductive capacity of the medium. Difference between charge and mass. Charge and mass. 1. The charge may be positive or negative. The mass is always positive. 2. Charge is conserved. Mass is not conserved, because mass can be converted into energy and vice versa. 3. Charge is quantized. Mass is not considered to be quantized. 4. Charge does not exist without mass. Mass can exist without net charge. 5. Charge does not vary with velocity. Mass increases with increasing velocity. 6. Charge is derived physical quantity. Mass is fundamental physical quantity. 7. SI unit of charge is Coulomb. SI unit of mass is kg. Now let's look some other properties of electric charges. 1. The electric charge is conserved. 2. The electric charge is quantized. 3. The charge is additive. 4. Like charges repel each other and unlike charges attract each other. 5. A charged body attracts light uncharged bodies. 6. Charge always reside on the outer surface of the conductor. 7. Charge always accumulate at the sharp edges on the conductor. 8. Magnitude of charges does not depend on its motion. 9. Charges produce magnetic field when they are in motion. 10. Charge is a scalar quantity. 11. Charge is scalar, its SI unit is Coulomb. Principle of superposition of electrostatic forces. It states that force on any charge due to a number of other charges is the vector sum of all the forces on that charge due to other charges taken one at a time. The individual forces are unaffected due to the presence of other charges. Application of principle of superposition to find the force between system of charges. Consider a system of n stationary charges. Let force on Q1 by Q2 is vector F12 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square into R12 cap. Force on Q1 by Q3 is vector F13 is equal to 1 by 4 pi epsilon naught into Q1 Q3 by R13 square into R13 cap. Similarly, force on Q1 by Qn is vector F1n is equal to 1 by 4 pi epsilon naught into Q1 Qn by R1n square into R1n cap. According to principle of superposition, net force on Q1 is vector F1 is equal to F12 plus F13 plus F14 plus up to plus F1n. On substituting the values, and take Q1 by 4 pi epsilon naught, common, finally we get vector F1 is equal to Q1 by 4 pi epsilon naught into summation I is equal to 2 to n, Qi by R1I square into R1I cap. This completes Coulomb's law. Next, electric field. It is the region in which the charged particles experience electrostatic force. Electric field strength, E. Electric field strength at a point in an electric field is the force experienced by the unit positive charge placed at that point. E is equal to force by charge. That is E is equal to F by Q naught. Expression for electric field in free space due to a point charge. Vector E is equal to 1 by 4 pi epsilon naught Q by R square into R cap, where epsilon naught is permittivity of free space. R is distance between Q and the point of consideration. Q is magnitude of the charge. R cap is unit vector in the direction of E. Note, for CET or NET. 1. C unit of electric field is Newton per Coulomb. 2. Electric field is scalar quantity. 3. Uniform electric field. It is the electric field in which unit positive charge experience the same force at all point. 4. Non-uniform electric field. It is the electric field in which unit positive charge experience different forces at different points. Source charge. It is the charge which produces the electric field at. The source charge can be a single charged or a group of charges or any continuous distribution of charges. Test charge. The charge that detects the effect of source charge is called test charge. Note 1. The magnitude of electric field depends only on source charge and the distance of the test charge from source charge. 2. It does not depend on the magnitude of test charge. 3. If the source charge is positive, the direction of electric field is directed radially outward from the source charge. 4. If the source charge is negative, the direction of electric field is directed radially inwards. Physical significance of electric field. Electric field E at any point around a charge is used to calculate the force F experienced by unit positive test charge Q naught at that point. That is, F is equal to E into Q naught. 1. Electric field is a vector quantity. 2. Electric field was first introduced by Faraday. 3. Electric field transport the energy. 4. It is a characteristic of system of charges and it does not depend on test charge. 5. It deals with the electromagnetic phenomena. Electric field lines or electric lines of force. It is a curved path drawn such that tangent at any point on it gives the direction of net electric field at that point. Or it is an imaginary path along which unit positive charge moves. 1. Electric field lines due to a single positive charge are directed radially outward. 2. Electric field lines due to a single negative charge are directed radially onward. 3. The electric field lines around two opposite charges are as shown in figure 4. The electric field lines around two same charges are as shown in figure. Properties of electric field lines. 1. The electric field lines, due to a pair of equal and opposite charges, start from the positive charge and ends at negative charge. 2. The electric field lines do not intersect each other. 3. The electric field lines do not form a closed loop. 4. The electric field lines are normal to the surface of charged conductor. 5. Due to isolated positive charge, the field line starts from charge ends at infinity. 6. Due to isolated negative charge, the field line starts from infinity ends at charge. Electric flux. The total number of electric field lines passing through the surface area held perpendicular to the direction of field lines is called electric flux. Or the product of component of electric field normal to the surface and area element. Delta phi is equal to summation of E delta S cos theta, where delta S is small area element of surface S. E is electric field. Theta is angle between E and normal to delta S. Delta phi is electric flux through delta S. SI unit is Newton per Coulomb per square meter. Electric flux is a scalar quantity. Next, electric field in terms of electric flux. Electric field is the electric flux per unit area. E is equal to electric flux by area. That is equal to phi by area. On taking area to left side, we get phi E is equal to E into area. The projection of area delta S normal to E is given by delta S cos theta. The electric flux through the area element delta S is given by delta phi is equal to E delta S cos theta. That is, delta phi is equal to vector E into delta S. Therefore, electric flux through a surface is defined as the dot product of electric field and area element. Note 1. Electric flux through small area delta S is given by delta phi is equal to E delta S cos theta. That is equal to delta phi is equal to vector E into delta S. 2. Total electric flux through entire surface is given. Delta phi is equal to summation of vector E into delta S. Or delta phi is equal to closed interval of E into delta S. 3. We have delta phi is equal to E delta S cos theta. Therefore, E is equal to delta phi by delta S cos theta. That is, electric field is the electric flux per unit normal area. 4. If theta is equal to 0 degree, then cos 0 degree is equal to 1. Therefore, delta phi is equal to summation of E delta S cos theta. Therefore, flux is maximum. 5. If theta is equal to 90 degree, then cos 0 degree is equal to 0. Therefore, delta phi is equal to 0. Therefore, flux is minimum. 6. Electric flux is scalar quantity. SI unit is Newton per square meter per Coulomb. Next, electric dipole. A set of two equal and opposite point charges separated by a small distance is called electric dipole. From diagram, a set of two equal and opposite point charges, that is, plus q and minus q, which is separated by a small distance, that is 2a. Note: net charge of an electric dipole is 0. Electric dipole moment. It is the product of magnitude of either charge of dipole and the distance between the two charges of the dipole. Dipole moment is equal to charge into distance. That is, P is equal to Q into 2A. SI unit is Coulomb meter, cm. Dipole moment is a vector quantity. Dimensional formula, a power 1, T power 1, L power 1. Another unit is dBA. 1 dBA is equal to 3.333 into 10 to the power minus 30 Coulomb meter. The net charge of an electric dipole is 0, but electric field is not 0. Vector form of dipole moment. Vector P is equal to Q into 2A P cap. The direction of dipole moment is directed from negative charge to positive charge along the dipole axis, as shown in figure. Note: the line joining the two charges is called as dipole axis. The midpoint of minus Q and plus Q is called the center of the dipole. Dipole moment is a vector quantity. Physical significance of dipole. The study of the electric dipole is 1. Used in the study of effect of electric field on the insulator. 2. Used in the study of radiation of energy from an antenna. Dipole field. It is the electric field produced by an electric dipole. The net charge of an electric dipole is 0, but electric field is not 0. Next, a very important derivation. Obtain an expression for the electric field at a point along the axis of dipole. Solution. From the figure, let plus Q and minus Q are the 2-point charges, which is separated by a distance to A. P is dipole moment acting from minus Q to plus Q. O is midpoint of dipole. Point M on the axis of electric dipole. And R is distance between O and M. The electric field at any general point P is obtained by adding the electric fields E minus Q due to the charge minus Q and E plus Q due to the charge plus Q by the parallelogram law of vectors. Therefore, electric field at M due to plus Q charge is E plus Q is equal to 1 by 4 pi epsilon naught into Q by R minus A whole square into P cap. Marks it as equation number 1. Electric field at M due to minus Q charge is E minus Q is equal to 1 by 4 pi epsilon naught into Q by R plus A whole square into P cap. Mark it as equation number 2. According to the principle of superposition, the total electric field at M is E is equal to E plus Q plus E minus Q. Mark it as equation number 3. Now, substitute equation 1 and equation 2 in equation 3. We get E is equal to 1 by 4 pi epsilon naught into Q by R minus A whole square minus 1 by 4 pi epsilon naught into Q by R plus A whole square. Now, take Q by 4 pi epsilon naught common. Then we get E is equal to Q by 4 pi epsilon naught into bracket 1 by R minus A whole square minus 1 by R plus A whole square. Therefore, on cross multiplying, E is equal to Q by 4 pi epsilon naught into bracket R plus A whole square minus R minus A whole square by R minus A whole square into R plus A whole square. Mark it as equation number 4. On simplifying, R plus A whole square minus R minus A whole square is equal to 4AR. Similarly, R minus A whole square into R plus A whole square is equal to R square minus a square, whole square. Substitute the values in equation 4. We get E is equal to Q by 4 pi epsilon naught into bracket 4AR by R square minus A square whole square. Therefore, E is equal to 1 by 4 pi epsilon naught into Q4AR by R square minus A square whole square. Now the above equation can be written as E is equal to 1 by 4 pi epsilon naught into Q2A to R by R square minus a square whole square. But Q2A is equal to P, that is dipole moment. On substituting P in above equation, we get E is equal to 1 by 4 pi epsilon naught into 2R P by R square minus A square whole square. Mark it as equation 5, where electric field and dipole are in same direction. For a large distance, R is much greater than A, then a square can be neglected. Therefore, equation 5 can be written as E is equal to 1 by 4 pi epsilon naught into 2R P by R square whole square. That is equal to E is equal to 1 by 4 pi epsilon naught into 2R P by R to the power 4. On cancelling numerator and denominator R, the final equation is E is equal to 1 by 4 pi epsilon naught into 2 P by R to the power 3. This equation is expression for the electric field at a point along the axis of dipole. In vector form, vector E is equal to 1 by 4 pi epsilon naught into 2 vector P by R to the power 3 into P cap. Next, obtain an expression for the electric field at a point on the equatorial plane of electric dipole. Solution. From the figure, plus Q and minus Q are 2-point charges, separated by a distance 2a. O is midpoint of dipoles. P is dipole moment acting from minus Q to plus Q. The electric field at any general point P is obtained by adding the electric fields E minus Q due to the charge minus Q and E plus Q due to the charge plus Q by the parallelogram law of vectors. Point M is on the perpendicular bisector of the axis of dipole. E plus Q cos theta is the component of E plus Q along ME. And E minus Q cos theta is the component of E minus Q along ME. And in triangle AOM, AM square is equal to R square plus A square. Similarly, in triangle BOM, BM square is equal to R square plus A square. Therefore, AM square is equal to BM square is equal to R square plus A square. Now, electric field at M due to plus Q charge is vector E plus Q is equal to 1 by 4 pi epsilon naught into Q by AM square into P cap. From the figure, AM square is equal to R square plus A square. Therefore, vector E plus Q is equal to 1 by 4 pi epsilon naught into Q by R square plus A square into P cap. Mark it as equation number 1. Electric field at M due to minus Q charge is vector E minus Q is equal to 1 by 4 pi epsilon naught into Q by BM square into P cap. From the figure, BM square is equal to R square plus A square. Therefore, vector E plus Q is equal to 1 by 4 pi epsilon naught into Q by R square plus A square into P cap. Mark it as equation number 2. Therefore, total electric field at M is E is equal to minus into bracket E plus Q cos theta plus E minus Q cos theta. Mark it as equation number 3. Take cos theta common. We get E is equal to minus into bracket E plus Q plus E minus Q into cos theta. Mark it as equation number 4. Substitute equation 1 and 2 in equation 4, we get E is equal to minus into bracket 1 by 4 pi epsilon naught into Q by R square plus a square into P cap plus 1 by 4 pi epsilon naught into Q by R square plus A square into P cap into cos theta. That is, E is equal to minus into bracket to Q by 4 pi epsilon naught into R square plus A square into cos theta into P cap. Equation number 5. But from figure, cos theta is equal to A by R square plus A square whole to the power 1 by 2. Substitute cos theta value in equation 5. E is equal to minus into bracket to Q by 4 pi epsilon naught into R square plus A square into A by R square plus a square whole to the power 1 by 2 into P cap. That is equal to E is equal to minus 1 by 4 pi epsilon naught into bracket P by R square plus A square whole to the power 3 by 2 into P cap. Because P is equal to Q into 2A. For a large distance, R is much greater than A, then a square can be neglected. Therefore, E is equal to minus 1 by 4 pi epsilon naught into bracket P by a cube into P cap. This is the expression for electric field at a point on the equatorial plane, where negative sign indicates that the electric field and dipole moment are in opposite directions. Note 1. At midpoint of dipole, E is equal to minus 1 by 4 pi epsilon naught into bracket P by A cube into P cap. 2. Electric field at a point on the dipole axis. E is equal to minus 1 by 4 pi epsilon naught into bracket to P by a cube into P cap. 3. Force acting on positive charge is along the electric field direction. The force acting on negative charge is opposite to the field direction. This ends the dipole moment. Next, physical significance of dipoles. 1. Most of the molecules have zero dipole moment. 2. However, they develop dipole moment when they are placed in an external electric field. But some molecules there is permanent electric dipole moment even in the absence of electric field. 3. The substance having this type of molecules are used in important applications in the presence or absence of external electric field. Note: dipole in uniform electric field. When an electric dipole is placed in uniform electric field, net force on the dipole is zero. When an electric dipole is placed in non-uniform electric field, net force on the dipole is not zero. A torque acts on the dipole placed in a uniform or non-uniform electric field till dipole is completely aligned along the direction of electric field. Next, expression for the torque, couple, acting on an electric dipole placed in a uniform electric field. From the figure, consider an electric dipole placed in a uniform electric field, E. Let plus Q and minus Q are two charges of dipole. P is dipole moment acting from minus Q to plus Q. 2A is distance between two charges. Theta is angle between the directions of E and P. Therefore, force acting on plus Q is F is equal to QE along E. Force acting on minus Q is F is equal to minus QE, opposite to E. These two forces, that is F plus Q and F minus Q, are two equal and opposite force acting on the dipole. As a result, torque is acting on the dipole. Therefore, torque is equal to magnitude of either force into perpendicular distance. That is, τ is equal to EQ into BO. Mark it as equation number 1. To find BO from triangle BOA, sin theta is equal to BO by AB. Therefore, BO is equal to AB sin theta. But AB is equal to 2A. Therefore, BO is equal to 2A sin theta. Mark it as equation number 2. Now, substitute equation 2 in equation 1. We get τ is equal to EQ into BO. That is, τ is equal to EQ into 2A sin theta. But Q into 2A is equal to P. Therefore, τ is equal to EP sin theta. This is the expression for torque acting on the dipole. Vector form of torque acting on electric dipole moment. Vector τ is equal to vector P into vector E. Note, we have τ is equal to EP sin theta. 1. If theta is equal to 0 degree, then sin theta is equal to 0. Therefore, τ is equal to 0. That is, torque acting on electric dipole is minimum. 2. If theta is equal to 90 degree, then sin theta is equal to 1. Therefore, τ is equal to EP. That is, torque acting on electric dipole is maximum. 3. If theta is equal to 180 degree, then sin theta is equal to 0. Therefore, τ is equal to 0. That is, torque acting on electric dipole is minimum. 4. SI unit of torque is Newton meter or Nm. 5. Torque is vector quantity. 6. Its direction is perpendicular to the plane containing P and E. 7. The direction of torque is given by right-handed screw and cork rule. Next, continuous charge distribution. 1. Linear charge density, denoted by lambda. It is defined as the charge per unit length. That is, linear charge density is equal to charge by length. That is, lambda is equal to delta Q by delta L. SI unit is Coulomb per meter. 2. Surface charge density, denoted by sigma. It is defined as the charge per unit area. Surface charge density is equal to charge by area. That is, sigma is equal to delta Q by delta S. SI unit is Coulomb per square meter. 3. Volume charge density, denoted by ρ. It is defined as the charge per unit volume. Volume charge density is equal to charge by volume. That is, ρ is equal to delta Q by delta V. SI unit is Coulomb per meter cube. Next, mention the expression for electric field due to continuous charge. Distribution. Electric field due to delta Q charge present in small volume element delta V is delta E is equal to 1 by 4 pi epsilon naught into delta Q by R square. Equation 1. But ρ is equal to delta Q by delta V. Therefore, delta Q is equal to ρ delta V. Equation 1 becomes delta E is equal to 1 by 4 pi epsilon naught into ρ delta V by R square. Electric field due to entire volume V is E is equal to summation of delta E. That is, E is equal to 1 by 4 pi epsilon naught summation of rho delta V by R square. This is the expression for electric field due to continuous charge distribution. Next, Gauss's law. Statement: the total electric flux through the closed surface in a free space is equal to 1 by epsilon naught times the net charge enclosed by the surface. That is, total electric flux is equal to Q by epsilon naught, where epsilon naught is absolute permittivity of free space. Note: Gaussian surface. It is an imaginary closed surface containing the charged body chosen for application of Gauss's law. Consider the Gaussian surface containing the charges as shown in figure. From Gauss's law, electric flux phi E is equal to Q1 plus, Q2 plus, Q3 by epsilon naught is equal to Q by epsilon naught, where Q is equal to Q1 plus, Q2 plus, Q3. Proof of Gauss's law. Consider an isolated positive point charge Q at O. Imagine a sphere of radius r with center O, as shown in the figure. The magnitude of electric field E is same at every point on the surface of the sphere, and it is directed radially outwards. Let delta S be the small area element on the surface of the sphere. S be the area of the sphere. Q be the charge enclosed by a sphere. Therefore, electric field at the surface is E is equal to 1 by 4 pi epsilon naught into Q by R square. Mark it as equation number 1. Therefore, small electric flux flows through delta S is given by delta phi is equal to E cos theta delta S. If theta is equal to 0 degree, then cos theta is equal to 1. That is, delta phi is equal to E into delta S. Mark it as equation number 2. Now, flux through the spherical Gaussian surface of area S is given by phi is equal to summation OD delta phi. That is equal to phi is equal to summation of E delta S. The equation can be written as phi is equal to E into summation of delta S. Mark it as equation number 3. Now, substitute equation 1 in 3. We get phi is equal to 1 by 4 pi epsilon naught into Q by R square into summation of delta S. But summation of delta S is equal to 4 pi R square. Therefore, phi is equal to 1 by 4 pi epsilon naught into Q by R square into 4 pi R square. On cancelling the terms, 4 pi R square from numerator and denominator, we get final equation, that is, phi is equal to Q by epsilon naught. This is called Gauss law. Significance of Gauss law. 1. Gauss law is true for any closed surface, no matter what its shape or size. 2. According to Gauss law, phi is equal to Q by epsilon naught. Here Q is the sum of all the charges enclosed by the surface. 3. The surface that we choose for the application of Gauss law is called Gaussian surface. 4. Gauss law is based on inverse square dependence on distance contained in Coulomb's law. 5. Gauss's law is applicable for both the stationary and moving charges. 6. Gauss's law is based on inverse square law. Next.
Applications of Gauss law. Using Gauss law. 1. Electric field due to infinite long straight uniformly charged wire can be found. 2. Electric field due to uniformly charged infinite sheet can be found. 3. Electric field due to a charged thin spherical shell can be found. Let's see one by one. 1. Derive an expression for electric field due to infinitely long straight uniformly charged wire using Gauss law. Solution. Consider an infinitely long straight charged wire. Let lambda is equal to linear charge density of wire. E is electric field at a point P. R is distance between wire and P. Draw a cylindrical Gaussian surface of radius r passing through point P as shown in figure. Let Q be the charge enclosed by the Gaussian cylinder. The electric field is radially outward. That is, perpendicular to wire. Therefore, flux through the end faces is zero. Because there are no components of electric field along the normal to the end faces. Therefore, phi is equal to E into area of curved surface. That is, phi is equal to E into 2 pi RL. Mark as equation 1. From Gauss's theorem, phi is equal to Q by epsilon naught. Mark as equation 2. But lambda is equal to charge by length. That is equal to Q by L. On equating, Q is equal to lambda L. Substitute in equation 2. We get phi is equal to lambda L by epsilon naught. Mark as equation 3. On comparing equation 1 and 3, we get E into 2 pi RL is equal to lambda L by epsilon naught. Therefore, E is equal to lambda L by 2 pi RL epsilon naught. On cancelling L from numerator and denominator, we get E is equal to 1 by 2 pi R into lambda by epsilon naught. Or, E is equal to lambda by 2 pi R epsilon naught. This is the expression for electric field due to a charged long wire. 2. Derive an expression for electric field due to a uniformly charged infinite plane sheet. From figure, E is electric field on either side of the sheet. R is distance between the sheet and each end face of cylinder. Let A is area of each end faces of Gaussian cylinder surface. Q is charge enclosed by the Gaussian cylinder surface. Sigma is surface charge density on sheet. The electric field lines are parallel to the curved surface of the Gaussian cylinder. Therefore, the electric flux through the curved surface is zero. The electric flux through the Gaussian cylindrical surface is phi is equal to flux through end phase 1 plus flux through end phase 2. That is, phi is equal to E into A plus E into A. Because phi is equal to E into area, which is equal to 2EA. Mark as equation 1. From Gauss's law, phi is equal to Q by epsilon naught. Equation 2. But sigma is equal to Q by A, which gives Q is equal to sigma into A. Therefore, equation 2 becomes phi is equal to sigma A by epsilon naught. Equation number 3. On comparing equation 1 and 3, we get 2EA is equal to sigma A by epsilon naught. Therefore, E is equal to sigma by 2 epsilon naught. This is the expression for electric field due to plane sheet. Note 1. In vector form, vector E is equal to sigma by 2 epsilon naught n cap, where n cap is unit vector. 2. E is directed outward if sigma is positive, that is Q is positive, and E is directed inward if sigma is negative, that is Q is negative. 3. E is independent of distance from plane sheet. Next, application 3. Derive an expression for electric field due to a charged thin spherical shell using Gauss law. Case 1. Electric field outside the shell. Consider a charged thin spherical shell. Let R is radius of spherical shell of center O. E is electric field at a point P. Q is charge on spherical shell. Sigma is surface charge density. Delta S is area element around the point P. P is point at distance R from O. The electric flux through the Gaussian surface is given by phi is equal to summation of E into delta S cos theta. Equation number 1. The angle theta between E and delta S is 0 degree, then cos 0 degree is equal to 1. From 1, phi is equal to summation of E into delta S. Equation number 2. Where area of Gaussian surface, summation of delta S is equal to 4 pi r square. Substitute in equation 2. We get phi is equal to E into 4 pi r square. Equation number 3. From Gauss's law, phi is equal to Q by epsilon naught. Equation number 4. On comparing equations 3 and 4, we get E into 4 pi r square is equal to Q by epsilon naught. That is equal to E is equal to 1 by 4 pi epsilon naught into Q by r square. Or E is equal to sigma r square by r square epsilon naught. Because Q is equal to sigma into 4 pi r square. This is the expression for electric field at a point P. Case 2. Electric field inside the shell. Consider a point P inside the spherical shell. Consider a Gaussian surface passing through point P as shown in figure. Electric flux through the Gaussian surface is phi is equal to E into 4 pi r square. Equation 1. According to Gauss law, phi is equal to Q by epsilon naught. Equation 2. From equation 1 and 2, E into 4 pi r square is equal to Q by epsilon naught. Charge enclosed by Gaussian surface. That is Q is equal to 0. No charge is present inside the shell. Therefore, E is equal to 0. That is, electric field due to a uniformly charged thin spherical shell is 0 at all points inside the shell. This ends chapter 1 all theory topics. Don't forget to share, subscribe the channel for more updates.